right, so it looks like we're live here, and I want to start today by looking at 10.46. Thanks for showing up. I know this is getting to be a grind. Let's go for it. So I'm going to share my screen, and let's take a look here. Whoops, there's the YouTube channel if you need it. So if you have any laggy issues today, you can always go back and watch these later. All right, and so, whoops, let's go right here. All right, so I wanted to start with 10.46. This one right here. Okay, so imagine you have a meter stick, and on top of it, you put a bunch of pennies, like is shown in the figure. And notice there is a pivot point. So what I did was I took a meter stick and I put a little skateboard bearing inside of it. And so it can actually swing very low friction bearing. Great. And now this is what's crazy. We're going to release this thing from rest. So you can imagine you're holding your finger under here, and then all of a sudden you let go of it and something bizarre happens. So that's what we want to study here. Okay. If we ignore the pennies completely, right? So just forget about the mass of the pennies. They're roughly uniformly distributed. Hopefully it's negligible. But what I want to do is determine the angular acceleration of the meter stick at the instant it's released. Now, for you as a physics student, hopefully you're thinking about what type of physics problem should I do? We've got a test coming next week. What are all the tools you have? You have forces, you have energy, you have momentum, we have center of mass, we have rotational kinematics, and we have torque, and moment of inertia, I guess, is in there too. When you see this problem, I'm hoping that two things come to your mind. When you see angular acceleration, I want you thinking either sum of torques equals I alpha, which is one possibility, or there's the delta theta equation equals 1/2 alpha t squared plus blah, blah, blah. What is it? Omega initial times t. Now, when you do this one, okay, maybe this is the part you don't have experience with yet. It turns out this is a terrible way to go. The reason why is angular acceleration is not constant for this. Usually when you have a swinging object, think about it. I'm going to stop for a second. This is important. Okay, please listen. If you have a swinging object, it's going to start out with a large rotational acceleration, a large alpha, but then when it gets to the bottom, think about it. When this is at the bottom of the swing, it's roughly constant speed because it's not going up or down that much. And so if you have an object that's swinging, alpha is not usually constant. If alpha is not constant, don't use kinematics. All right. We can talk about exception in this week's code, but yeah, whatever. Before I go on, I want to make sure that's clear. All right. If you have any questions, throw it in the chat. I'm just going to pause for just a second. I'll bring up my screen here. Do not use kinematics on this puppy right here. As this swings, the amount of gravitational force stays the same, but the amount of gravitational torque changes. All right. All right. I'm going to assume you're all good. Okay. So let's go ahead and just look at the solution really quick and see what we can learn from it. All right. So let me get rid of that. Oh, I got to get rid of that. Okay. And we'll go over here to the solution. All right. So like I mentioned, there is a video that you can watch on your own later, and you can see that I'm not lying to you about all this. But take a look here. There are two forces that act on the ruler. The most important one is this mg, right? So we know that there's mg, and that's going to act at the center of the rod. Notice something that is different from chapter 5 and 6 free body diagrams. I'm actually showing the entire object now because for torque purposes, if we want to understand torque, we not only need to know about the force existing, we need to know where it is, because now this L over 2 is important for doing the torque calculation. All right. And all right, I'm going to mention this other force too. This thing is not in free fall. There's another force here, this R vector. Okay. R is called the reaction force. This is something we're going to study at length in chapter 12. So for now, it suffices to say that there is a force acting at the pivot, and we're going to call that force a reaction force. The pivot is reacting to all the other forces that are acting on the rod. It's not quite the same thing as Newton's third law, but it's similar. So let's leave it at that. Now, one thing that you notice, because the reaction force is located at the pivot, regardless of the direction of the reaction force actually points, or the line of action for the reaction force runs through the pivot. All right, let's do the calculation now. So the torques, that's going to come from the force arrows. So here, if I talk about the torque due to mg, right, I need the distance r perpendicular times mg. In this case, r perpendicular is L over 2. That is the lever arm. It's the perpendicular distance, right? Or it's the distance from the pivot to the line of action. R perpendicular is this distance right here. Okay. And now in this case, the angle is 90. Some of you might be saying, wait a minute, I thought I had to use torque equals R mg, which is the force, times sine of some angle. You are right. That is another way that would work, because in this case, notice the angle between them is 90 degrees, right? In this case, we have a 90-degree angle right there between the, all right. And so here R, the distance between them is L over 2. So in this special case, R perpendicular and R happen to be the same because the angle is 90 degrees. All right, we're starting easy. If you have any questions, dump them in the chat. I noticed that Trey is here. Trey will try and help you, and I'll check in periodically. So definitely, if you have any questions at all, dump them in the chat. All right. So that is this side of the equation. The torque is the force times the distance times sine of 90. Great. Moment of inertia. I looked that up in my table on the exam equation sheet. For a rod, it's usually 1/12 or 1/3. From experience, I know if the pivot is at the center, I use 1/12. If the pivot is at the end, you use 1/3 ml squared. All right. And then alpha, that's, I think, what we were asked to find, wasn't it? In the question that said, determine angular acceleration. That's what find. All right. I think it's pretty easy. You see that one of these L's cancels that, you get a 3. All right. Second to make sure that makes sense. Okay. Looks like everybody, if you have any questions, throw them out in the chat. Back into the problem. All right, so let's look at the next part. Angular, looks like there's a question in the chat. I'll get there in just a second. So next we're going to determine the acceleration of a point on the meter stick. If we're looking for the acceleration of a point on the meter stick, that's going to be a little bit different. And I'm assuming we're still at the instant it is released. All right, so matter here in just a second. I'll check that here. Okay, looks like Troy got it. If that didn't make yeah, at center mass. Yeah, all right. Good job, guys. All right, so let's go into this one. If I want the acceleration, remember, angular acceleration is alpha. Acceleration is actually a total. I can't read that at all, so get that over here. That's actually a total. in this case, we actually have kind of a special scenario here. A total in general is equal to AC squared plus A tan squared square rooted. And so in this case, because it's released from rest, let me get something out of here. All right. Oh, come on. When you see released from rest, the omega initial equals 0. And most of you are probably okay with that. But if omega's initial is 0, this is also 0 because that's r omega squared. So this is also going to go to 0 initially. Obviously, it will not remain 0. That's a big indicator that acceleration here is not constant. And so we're going to, anyways, all right, more later. Okay. So how do I go about and do this? I'm going to go to the solution now. All right. So in this case, I tried to use what I just told you. And notice this may not look like it initially, but it is the same equation here. If I say that A tan is equal to R alpha, in this particular problem, if I go over here some distance x, my radius is equal to x, right? X is now the distance from the pivot. So if you go over x centimeters, and then all you have to do is you say a tan, which is the only component of acceleration present at the beginning, should equal x times alpha, and that's it. That's pretty cool. All right, I'm going to stop there and look at, let me clear this out. If you have questions, go ahead, throw them in the chat, but I'm going to do the next part. This is the cool part. Which pennies remain in contact with the rod just after the release? Okay, so let's go back and look at this thing. And whoops, I want the solution here. I'll get the question in the chat in just a second. Think about this. You've got, let me go to here. Whoops. All right, here's my equation. Notice anytime x gets bigger than 2/3 L, the acceleration of the rod is going to be greater than g. Again, this line right here, an acceleration of a point on the rod is greater than g anytime x in this equation is bigger than 2/3. So if you shoved in 2/3 for x, you get g. If you stick in a value bigger than that, you get an acceleration bigger than g. That means the rod is going to accelerate away from the pennies, and the pennies above it will be in free fall for all pennies above about 70 centimeters. And if you don't believe me, watch the video, because I'm not coming in to get coronavirus just to show you that some pennies on a stick. But it actually works. It's pretty darn cool. So thanks to some student a couple years ago for helping me make that video so you could watch it after class tonight. It's one of my favorite demos. All right. Let's see what else we've got there. Oh, and there was a chat question. No. Okay. Alpha is angular accel. So I'm adding questions. A tan equals radius times. Give me just a second. So alpha is the angular acceleration, and a tangential is it's the acceleration of a point particle going around in the circle. So this is very sneaky. Yeah. So each point of the rod has the same alpha, but each point of the rod has a different a tan. Just to make sure you got that, every point on the rod is rotating the same rate, and the same rotational acceleration. So every point on the rod has the same delta theta, every point has the same omega, every point has the same alpha. But as you get farther away, the points that are farther away literally have to move more to stay in the same circle, right? If it's going to go the same angle, it's got to cover more ground. And so that's why they have a different A, but they have the same alpha. That's a big, big thing to get. So hopefully that makes sense. Yeah, that's a big deal. So always watch out for alpha versus A. All right. All right, this is a cool one. So I'm looking at part D. Let me share the screen now. All right. Part D. So a short time later, the rod's still swinging downwards, but it's angled. Okay. So if the rod is swinging down and it's angled, would you expect alpha to increase, decrease, or stay the same? I already told you that it's not constant, but just think to yourself, what should happen a half second later? It's going to take me a second to draw it. So you think, well, I draw. All right, so I've had a second to draw. Hopefully you've had a second to think. Let's say a tiny bit later, it's rotated what looks like about 20, maybe 30 degrees. There's probably about 20. So imagine this rod has rotated 20 degrees. The force on it has not changed. mg is still exactly the same. The distance between the pivot point and the point where that force is applied, the center of mass, has not changed. So we know that the r vector hasn't changed, and we know that mg hasn't changed. Has the torque changed? Yes. There's a different angle. And if you have a different torque, you should have a different alpha. So just cheating and going over to the solution, whoops, over here. Sorry, now you can see them both kind of laid on top of each other here. In the original one, you had a 90 degree. Now we've got either this blue one or this purple one. Think to yourself, which angle do you need to use to get the torque? Do you need to use the light blue one or that kind of light purple one? Think to yourself. Either one. You can use either one. Torque is, that's the only nice thing about torque. You could use the blue angle or the purple angle. The point being, when you plug into the equation here, if I do the torque equals radius times mg times sine of some angle, let's say it ends up being, I don't know, about 70 degrees or something like that. Who knows if that's right? Hopefully you can see immediately that sine of 70 is going to be a smaller number than sine of 90, because sine of 90 is as big as sine is going to get. Said another way, anytime one of the components is parallel to the radius vector, you get a smaller torque, right? Anytime the force is perpendicular, you get a maximum torque. Anytime it's got some angle component that's parallel, you get less torque. Point being, we have less torque, you should get less alpha. Take the extreme case when this thing is hanging straight down. In the case where it's hanging straight down, think about this silly looking one, right? Well, there's going to be a reaction force straight up. There's going to be mg straight down. And in this case, hopefully you agree, because mg, the line of action goes right through the pivot, there's actually no torque at the bottom. And that's why alpha is equal to 0 at the bottom. And that's why earlier in the semester we said things that are swinging down at the bottom have no tangential acceleration down at the bottom. So this is making sense. All right. So moral of the story here, the angle matters. And when you have a swinging object, you can't use constant kinematics because, it's if you have constant, we don't have constant alpha in these problems. All right, let me clear that out. Almost done with this one. Let's see what else is in there. All right. Ooh, this is a fun one. If you used a 2-meter rod instead of a normal meter stick, let's go think about how this is affected. The key when trying to answer something like part E is not to guess. It's fun to guess, but then try to use an equation to guide our reasoning. Since we already wrote one, let's go look at it. This was our equation. Aha! If I use a longer rod, the length does matter. The bigger the rod is, the smaller the angular acceleration. And this kind of makes sense with maybe some intuition you have. The larger an object is, maybe the easier or harder it is to get rolling. But I rarely trust my intuition in physics problems unless I can also back it up with an equation. So here, this allows us to see that as length increases, we expect a smaller angular acceleration. So that's kind of interesting. All right, that's cool. Let's go back and see what else we've got. Okay, that's cool. All right. Well, let's not worry about F if you want to. That's just for fun. That's good enough. All right, you can do part F on your own. I'm going to stop the share for a second and let's see. All right, any questions so far? You're probably good. Question, Nick, or no? Or just connecting there or something? Okay. All right, so I'm going to go ahead and plow through, as exciting as it may be, and let's maybe take a look at 10.47 really quick. All right. All right. Man, I really wish we were in class right now, people. These two are really fun to do live. It's really exciting, and now it's like super boring. So sorry about that. What can you do? Anyways, this is a variation on the previous one. And this is a good problem because you're forced to deal with the angles. Yeah. Where is that chat? I can't see the chat right now. Anyways, I'll catch up with the chat in just a second here. Sorry. Trey, if you're on it, you got it. But so this shows you what's going to happen here if you angle this situation. And so I'm going to let you try and handle this one on your own. And I am going to, there is one extra step. Part A is not like the most important thing in the world. It's just a little bit of geometry. Notice that, so I'll talk about that really quick. Yes, still doing chapter 10 on Wednesday. So no new material from chapter 11. Okay. After you take your test and do your interview, you should try to get ahead and do week 15 videos, but that's, yeah. Week 10 this is where I was saving our time all semester, trying to rush so that we'd have extra right now. Good question. All right. Let me get this. Okay. All right, there we go. All right, so let me get back to this one really quick. In this case, notice the following. You want the cup to end up here. The cup is going to follow the solid green line path, but you need to make sure you put it here. Well, so what is this distance here? I guess you could say, in this case, well, how about like this? This side right here is L cosine theta. Hopefully you see that. So the whole thing right here is L. All the way out there is L. So if this is theta and that whole thing is L, this side's L cosine theta. So if you put the cup at L cosine theta, when it falls down, it's gonna end up in the right spot. So this triangle that I drew originally was actually not useful. So I'm gonna take that out of there. All right, so that, don't worry about part A, but if so, that's cool. Now, this is an important question right here, though. Oops. Right here. What is the largest angle we can use such that the cup has an acceleration greater than g? Now think about this. If we put it horizontal, we just saw in the last problem that you actually get maximum alpha when the weight is at a right angle to the board. So, and we also saw that if you put it straight up in the air, you get no alpha. Think about it. If this was perfectly balanced, the weight would go through the pivot. So we know that this is a large alpha down here. This is large alpha. Alpha is large. And up here, alpha is small. So there's got to be some angle that allows us to still get acceleration greater than g. So, whoops, let me clear those annotations. So again, I want to leave most of this one for you at home, but looking at this problem, you could see that there's a free body diagram, and you're going to have to analyze this at home on your own, but you could see it's very similar, just mixing it up a different way, and we get this cosine squared in there, which is kind of special. All right. Going back to this one, I think that's enough. You can get the rest of that on your own. All right. And so we're up to our next big topic. So before I do that, I am going to stop the share just in case. All right. The next topic I want to cover is kinematics with rotation. We've talked about moment of inertia, which is sort of like center of mass. We've talked about torque, which is kind of like force. And now I want to see how can we do problems using energy, but add in the rotation crap. So to remind you, let's go take a look. All right. So if we're using energy, it's exactly the same as chapter 8, which hopefully you've done a lot of. And now there's different types of energy problems. So before we get too crazy, there's swinging motion, which is like the ones we've just done. Okay, give me a second here. So we've got a couple of those. There's going to be a pulley spins while some blocks rotate. We'll discuss that in a minute. Oh, there's some more torque. And then I think there's rolling motion, which is probably the hardest of the bunch. So those are the types of problems we are going to handle with energy: swinging, rolling, and some pulley problems, okay? So let's start simple and just do swinging motion and see if we can understand that. We're going to start doing energy with rotation and swinging motion. Now, earlier in the semester, we did this like if you had a ball on a string, we just set as 1/2 mv squared and everything worked. That doesn't work very well if you have a pendulum now. So anytime you have an object other than a point mass on a string, the old method doesn't work. Oh, crap. I'm not screen sharing, am I? Damn it. Sorry about that. Forgot to hit the screen share button. All right, here we go. Sorry about that. Rotation and swinging motion. Sorry, I'm right here. This is page 73. Sorry, I forgot the screen share. I was dumb. All right. This is a gravitational potential energy initial. This is gravitational potential energy final. That's nearly identical to what we did before, but notice this huge deal here. You need the height of the center of mass. Oh, yeah. Yeah, you're going to love it. And you also need the final height of the center of mass. Notice we don't need the mass of one object, we need the total mass in both of those. Oh boy. So that's basically the same thing though. That's just U sub G for gravity, or sometimes we call it gravitational potential energy. Sometimes we called it GPE. This term, the next one in there, let me get blue, let's say. This is called RKE, or rotational kinetic energy. So it's the energy associated with the spinning or swinging motion. So spinning or swinging, right? So again, this is not that different than saying U initial plus K initial equals U final plus K final. It's exactly that. And finally, don't forget, sometimes we have this devious little issue here. This doesn't actually show up a lot in the swinging motion problems, but it may show up in a later problem, as I'll address later. But that's friction. We're going to ignore friction on the pulleys usually, or on the axles. All right. Summary of this. Gravitational energy, you got to do it at the center of mass. Okay. You cannot just go wherever you want now. It's got to be at the center of mass. For angles from the vertical, just like this one, remember this formula and have it memorized, because deriving this on a test will chew up the clock. If you want to know where that is derived, let me look it up for you really quick. I know the page number really quick. Where is it? Page 19. This is page 19 in your workbook, volume 2. So page 19 of volume 2, I have a big picture and I derived that. But we use it so much, you should memorize it. Okay. All right. And then I will get to the questions in just a second. This is what I was saying. The work is 0 because we're going to ignore axle friction. Forces towards the center of motion do no work. And then sort of what Jay was talking about earlier, I think it was Jay or maybe it was Jerry. The translational velocity of any point is given by V equals R omega. Remember, every point is going to be swinging with the same RPMs, the same omega, but every point is going to have a different V. Points farther out on the rod have to travel a greater distance to cover the same angle. I'm going to check the chat really quick. Okay, so you could have a spring or a stretch and a rotation, and I can actually show you that. An example of such a problem would be 10.54, where there's a block that's attached to a spring, and then the pulley is rotating. So we can actually get springs and rotation in the same problem. And it's not that hard. You just add in a 1/2 kx squared. So 10.54 is that exact problem, 10.54. Now, the other thing that you could do is you could have a pendulum made out of a spring that's swinging. And the way I would solve that is coding it. It's just not feasible without coding it. All right. Yeah. Yep. Yeah, cool. There's another thing. It's unfortunate that I usually bring up at this time. You have a bungee cord and you're going to go bungee jumping off a bridge. You can actually check the bungee cord, and if you fall straight down, well, that's perfect. You've got everything rated correctly. But if you have a swing, so some people would do these swings in their bungee, and they forgot to account for the fact that, well, you need extra tension to make the thing go in a circle, and you can kill people that way. And people have done that. The people have died because they didn't account for the fact that it's a spring, and because it's a trickier calculation, and they screwed it up and killed some people. So we'll stay away from that one for right now. All right. Yeah, always worry about that rotation with your springs if you do have that in a real world problem. All right, good. Where was I? Oh, page 73. All right, so let's go take a look at some problem now, all right? Yeah, it's a good question. All right, so here's the graph that we're going to use, page 73. We want to use this crap here to do a problem. Let's just keep it simple first. Let's do this problem. 10.48. Don't think too hard. We have a uniform rod, mass M, length L, supported by a pivot with negligible axial friction. Woohoo! Negligible axial friction. That says work non-con equals 0. Negligible axial friction, no work. Okay. The rod is initially held at some angle here. It's released from rest. Hey, released from rest. I know that one. Released from rest says the initial rotation rate is 0. All right. What is the speed of the end of the rod at the lowest point in the swing? Okay, read that carefully. And I'm going to write this down, omega or V. That's my question to you. Think to yourself, what is the speed of the end of the rod? That is omega. Sorry, I said omega, but it's V. Okay. It obviously relates to that. So it turns out what we're trying to do in this problem is we're trying to get the speed of this thing at the end of the problem. This is going to be rotating with some rate omega. But the end of the rod is going to be moving this way with some speed V equals radius from the pivot times omega. So we're going to try and figure out V, but it's easier to come up here and get this first. If I can solve for omega final, I can plug that in and get the velocity. That's our sketch. And just in case that was lagging, I want to go through this again. I have a question that asks about speed. When it's asked about speed, think energy. Okay. If it asks about alpha, torque. If it asks about speed, think about energy. Okay. It's usually to go, not always. If we have a speed question, I'm thinking, okay, I have a swinging object. I know that Mr. Jorsted said, think about energy because it says speed. I'm going to get this. I know that this goes to 0. All right. At the bottom of the swing, that's probably going to go to 0. The work is 0. So it's basically get the center of mass and solve for omega. All right. Let's go look at the problem and see what's up. Okay. Whoops. Here we go. All right. Oh, there's that picture right there. Why didn't I just tell you to open the, well, whatever. Okay. The geometry of the initial and final positions are shown here. Just to be clear. Okay, here's the center of the rod initially. Here's the center of the rod at the end. And notice the radius to the center of mass, it's not L because the center is at L over 2. Agreed? L over 2. Again, the center of mass of the rod is not at the end. That's something you've got to get. And I'll get to the chat in a second, but maybe Trey can hit it for me. So, all right. Here's my energy equation. Notice that with air resistance and action friction are negligible. Tension in the rod, if you were worried about that, that's always perpendicular displacement. So there's no work non-conservative. So the work non-con equals 0. That's what all that crap in red is. All right. All right. There we go. This is 0 because initially at rest. This is 0 because in the final state, I'm going to set this as height equals 0. You are free to choose whatever height you want to call 0. So I call the lowest point of the center of mass 0. Got it. Now, here in this case, M is the total mass, which I think we only had one mass in this case. It was a rod with a point mass on it. So there's the height. Notice this little height right here is this right here. All right. And over here, I notice we still get a 1/3. Hey everybody, if you're kind of tired of listening to me, try to listen right now. Try to listen right now. One of the more common mistakes people make is they'll see the fraction for the moment of inertia and they'll forget the 1/2 is there from the energy. So it's getting pretty sloppy. I just want to point out this 1/3 comes from the moment of inertia table. This 1/2 comes from the energy definition right here. So you usually get two fractions on one of the sides. All right, from there, it looks like I didn't solve for the right thing, did I? It looks like I found omega final, but what was I asking for? I have forgotten already. Let's go back and look. Whoops. In this case, I asked for the speed of the end of the rod, so I didn't answer this correctly. Oh, I'm glad we saw this. So I should finish this problem out. There's just one more thing here. V final, this is one I always do in class, so I never noticed the typo. What is the distance? It's the full distance L. That's a big L. So when you do this, V final is actually going to look like, and I'll post it, but when you multiply by L, you got an L inside, it's going to be 3G, and the L outside becomes an L squared, which cancels one. It's going to be times minus. That is the correct answer, not what I wrote. That is the correct answer, not what I wrote myself. Piece of paper. And now I've been away from the chat for a while. I really apologize from that. That was part A. I'm going to go verify that the chat is doing all right. Okay, cool. And it sounds like Trey got it. Okay, cool. Yep. All right. Whew. Questions? Okay. I'm going to go ahead and see if I can look at more parts of this one. All right. So does this answer make sense when theta goes to 0? That's a great question to ask about this one. So, oh, I forgot my screen share. Let me do that. Oh my gosh, so many windows. Okay, there we go. All right, so I'm looking at this. Does the answer make sense? I think so. Let's go look at the solution. Hopefully it does. As theta goes to 0, cosine theta goes to 1, which means this goes to 0, which means omega goes to 0, which means V goes to 0. So if you start this thing at the bottom, the speed is 0 at the bottom. Sweet. All right. Let's go back and take a look at the next part. Just after release, which way does acceleration of the end of the rod point? Okay, this is a good one. All right, so here's the point. Right after you release it, remember that omega is equal to 0 and alpha is not equal to 0. This thing tells us that AC equals 0, and this one tells us A tan is not 0. That's what I was hoping you would get out of that. I don't know if that was clear, but that's what I was hoping. So it's actually going to be straight this way. At the bottom of the swing, it's exactly the opposite, right? The acceleration points straight up. Hopefully this sounds vaguely familiar because we did this a couple of months ago, if you can believe that. We talked about a ball swinging and we said, oh, initially it's all tangential. And then at the end, it's at the bottom of the swing, it's all centripetal. All right. All right. So I'm looking at part E now. Moving on. Theta is 90. Oh, I'm going to clear all my drawings here. So theta is 90 basically means start with the rod up here, right? So now this would be theta equals 90 degrees all the way up. Okay, we're starting with all the way up in part E. Determine the translational speed of the tip of the rod at the, okay, got it. So if I talk about translational speed, that's V, okay? All right. And I guess one thing I could have done here is to make this match up, I could call this rotational speed. And that would make this, so that's probably what I meant to say in the question and just left it out. So that's bad, but all right, whatever. All right. All right. But the point being here, this one's a little surprising. Okay. You might say, should it be bigger or smaller than this right here? This is the free fall result for a rod that falls distance L, right? If you have an object that is in free fall, right? If I just say mgh equals 1/2 mv squared, that's dropping a rock from an initial height h, you get v equals the square root of 2gh. So you might be wondering, is this one going to be faster or slower than that? And when we look at the solution, it might shock you. I don't know, maybe not. Look at this. It's actually falling faster than free fall. That is crazy, right? Now, think about how weird this is, people. You're putting an extra force upwards on the rod, and the bottom of the rod is actually falling faster than if there was no upward force on the rod. That's crazy, isn't it? Just have fun with it and savor it and let it soak in like a nice tri-tip marinade, okay? Or some tofu marinade if you're vegetarian, all right? Anyways, it's one of the coolest things out there. I don't know, whatever. Okay. Yeah, let's go ahead. Yeah. So is that because the center of mass of the rod? Okay. So yeah, if the center of mass was at the end of the rod, I think it would be exactly the same. But in this case, remember, points near the, okay, so let me get a picture. Let's go to here. Now remember what's happening here. They're all rotating. They all have the same omega. All right. Now what will happen here is this point is barely moving at all. This point's moving a little faster. This point's moving a little faster, etc. And each point on the rod is going to be moving faster and faster. Obviously, it has to be moving this fast when it gets to the bottom of the swing. And then just like before, we saw that somewhere right around this 2/3 point, there's this weird transition. But the fact remains is you actually have less total kinetic energy now. Just because the point at the bottom is moving faster doesn't mean that on average, they're all moving a lot slower than this. So on average, most points on the rod are going a lot slower than that. Okay. And I think it's only these last, so 2/3 of the points are going slower than that, and 1/3 are going faster than that. So on average, it's a much lower kinetic energy. It just so happens that the point at the end is actually going faster than free fall. All right. On average, this thing is not having, yeah, anyway, all right. Let me go back to see if that addressed that question. Isn't that crazy? Okay, yeah. Yeah, that's a great way to say it too, Trey. I like it. Look at it from the center mass perspective. It's trying to fall straight down, and the pivot is trying to prevent it from falling straight down. Yeah, so it's going to, yeah. All right. Good stuff. All right. 10.49 is really cool. It's a demo I do. We're not in class, so shucks. All right. Let's take a look at 10.50, everybody. 10.50. All right. All right. This is where it starts to get real, people. 10.50 and 10.51. So these are kind of exam level difficulty here. These are pretty gnarly. So notice, for example, parts A and B look pretty darn similar. This is the full thing. Now you've got an angle. We've got a rod with some mass, but we also have a point mass stuck on top of it. There's negligible axial friction. So that says that work is going to equal 0. Object is initially released from rest. So it's almost the same problem, but now before you start anything, you need to figure out the radius of the center of mass, because that was crucial in the last problem for getting the heights. We need this distance from the pivot to the center of mass. Well, we've got this one right here, and we've got this one right here. And because they're equal mass, it should be somewhere in between there. I'm going to pop over to the solution just to get a look at it, because it'll be faster than me writing the equations. All right. Whoops, that's 10.49. Okay, sorry. Looks like I've got some pretty good notes in there for 10.49 people. So you might actually do 10.49 and read the notes. But here it is. This is this one. We're looking at 10.50. All right. This is for the rod, right? And this is for the point mass. The point, and remember, the pivot is right here. So, and then this is the total mass, right? They're each m in this case. So when you do all the work here, we get this is the radius to the center of mass. That means for part B, the height of the center of mass needs to use this disgusting formula. It's not that hard to write it down. It's just annoying to work with. All right. And it's the same exact problem. So anytime you have a swinging motion, if you have this memorized, it will save you a few minutes. I have initial gravitational, initial rotational, no work because there was the negligible axial friction. I have a final gravitational and final moment of inertia. Oh, crap. The rotational, this moment of inertia piece is not easy either, is it? Okay. Now I need the moment of inertia of this whole thing. Let me get a different color here. So I've got moment of inertia of this. I'll call that I2. And then I've got moment of inertia of the entire thing here. The rod, that's I1. So now notice the moment of inertia here. This is the part from I1. That was the rod. That's exactly the same as last time. But we also have this extra term in the moment of inertia from the point mass. And like I said before, don't forget this 1/2 here came from this 1/2 right here. Woo! Other than that, the problem's exactly the same. just those massively complicated changes. Other than that, it's exactly the same, right? Oh my gosh, whatever. But it's actually pretty followable, I hope. I paused there. Let me see. I don't know. What do you think? Questions on that? Maybe I erased the screen too quickly. I'll bring it back. All right. It's some crazy looking thing. And this is a cool way to check your work. Think about it. Wait, is it 43? I think that needs to be updated now. That's 10.48 now. Okay. What is that? 10.50B? All right. Got it. Sorry, I made a note to myself there. All right. And so there we go. Hopefully that makes some sense. And hopefully you had a second to catch up to that. I might just pause for a second and see. I don't want to just fly past it. There's some questions in the chat. Sweet. Okay, it looks like, okay. Yeah, maybe I can't. I'll fix it anyways, but yeah. Okay, so Jay's question, height final cancels out the first term on the right side. Oh, at the, yeah, remember at the end. Okay, maybe. Hey, yep. Okay, you got it. Trey's on it. Okay, cool. I don't need to say anything. Remember, that's your choice too, right? You choose what point you call 0. And boy, it sure would be nice to call this height final equals 0, because then we don't have to deal with negative heights. So you get to choose. You could also call the initial height 0. You could call this height 0, and that would just be less fun. Yeah. By less fun, I mean more work for the same amount of answer. Yeah, good stuff. Good stuff. All right. I'm going to go ahead and read the question and continue. Whoops. Come on now. Oh, yeah. So this was actually a lab. So maybe you can be glad COVID came so you weren't the one having to do this in lab. But yeah, this one is very shocking to me. Okay. So let's go read the question associated with this. Plot the rotation rate at the bottom of the swing versus X. It's not that bad. We have an equation that's got X in it. So let's go look at that. Here's an equation for omega that has X in it. So the idea is you could change the value of X and change the location of the point mass. And this is what students had to do in lab. They would move the point mass. And then my question for the class was always this bonus one right here. What value of X gives the maximum rotation rate at the bottom of the swing? Is it X equals 0? If it's X equals 0, that would be like putting the point mass right here on the pivot. That keeps the moment of inertia as small as possible, should make it easy to rotate. You could put it way out here at the end. Now that gives you a large moment of inertia because the point mass is now far, but it also gives you more torque, right? Because it's putting the center of mass. So we're changing both the center of mass and the moment of inertia as you move this thing back and forth. So it's not obvious what value it should be. And okay, there's a chat question there. It's not L over 2. It's some weird ass point. That's the answer. Some crazy spot. Look at this. It's right here. In this particular example, it's right about here. At about a quarter of the length of the rod. Oh, right here, 0.264 meters. So if you're using a meter stick, you get this weird combination. As you move the point mass out, you increase the moment of inertia, but not significantly. At the same time, you're adding to the torque by shifting the center of mass over dramatically. However, at some point, once you get far enough out, you're increasing the moment of inertia more than you are adding to the torque. And so it turns out these two competing things, for every system, they're going to balance out at some weird point. And it's not like, yeah, if you use a point mass that's 2m, I think it actually shifts even a little bit lower. So depending on the point mass you stick on there, it's not always going to be at the same point. That's, to me, was really fun to discover. It got me too. So if it got you, it got me too. Don't worry about it. All right. And then I bet you could understand part E right now. Should the speed of the point mass be square root of 2gl at the bottom? No way. This is not a free fall problem. Okay. Again, what am I saying? This question. Should it be square root of 2gl at the bottom? This is not true at all for two reasons. One, the center of mass did not fall distance 8, or did not fall L. Okay, think about it. The center of mass is probably right about here. It's only falling this tiny amount right here. the center of mass is falling less than L over 2, right? It's probably falling, I don't know. Okay, maybe it would, okay, it depends a little bit if we go up to 90 degrees, but yeah. So it's not falling the full distance. That's one thing. And it's not in free fall. This is not applicable to these problems anymore. This is not a free fall. There's another force from the pivot, and there's mg acting at the center mass. Side note, which of these forces should be bigger, or are they equal to each other? And then I'll get the chat question in just a second. Think, do you think the reaction force, or mg, is bigger, or are they balanced? Keep in mind, this thing is rotating here. It's not accelerating, it's not translating up and down. It is rotating. So I'll let you think for a minute. In this case, technically, R is less than mg. All right? They're not balanced. The center of mass is technically accelerating downwards. Think about the y coordinate of the center of mass. It is actually getting lower. And so that means there's a net downwards force on the object. So mg should be bigger than the reaction force. Yeah, anyways. All right. I'm going to go get to that chat question just in case. Oh, for D. So NM. Oh, that probably means never mind, huh? Sorry, Nick. My bad. Okay, yep. Right on. Okay, cool. All right. What do you think? Is that making any sense? I have no idea. I'm gonna stop the share for a second. So I hope this is helping. I get, I'm looking at a bunch of names and dog pictures. So if this is being useful, just let me know right now. And if not, just I don't know. Just give me some feedback so I can tell if I should keep doing this kind of crap or not. Looks like I'm getting a couple thumbs up. All right. All right. Okay, cool. Yeah, and it's tricky. I'm trying to do some of it and leave you like one or two pieces to do, but like give you big head starts just to cut the amount of work you have to do. So that's my goal, and I hope I can do that. Seems like it's doing something. Everybody, let's take a look at 1051 and then take a break. So we're going to look at 1051, all right? I'm going to bring it up on screen. So I've kind of told you the last two. So maybe try not to look at the solutions right away. All right. Let's see what you think would be weird about this problem. And what are going to be the parts that are tricky? Okay. Disk, blah, blah, blah. You have a hole of radius r over 2 cut from it as shown. The disc is then attached to an axle. Negligible friction. Love that. All right. Okay, got it. The disc with the hole is released from rest. And now think to yourself, when you release it, does it make sense to you that the hole rotates upwards? I hope that makes sense. Again, if you think about it, I'm going to try and draw the center of mass here. I'm guessing that the center of mass is probably about right there. When you cut the hole out, it shifts the center of mass the opposite way. So now when it falls down, look at this. Hopefully you agree the center of mass is falling, which is typical for a swinging object. The center of mass goes down a little bit as this thing swings. So in this sense, it's exactly the same as the last problem. The center of mass, when you release it, it's going to be an energy problem, but we're going to have a lot of heavy lifting to get to that point. So all the work that you did in chapter 9 on center mass and holes is going to come in handy. Oh boy. All right. So now a uniform disk has mass m. Whenever you have a hole, it's really annoying. You got to find out, is this the mass with the hole or without? According to this is without hole, right? So the mass of the entire disk is m, and you're cutting out a chunk. So now my mass is not m anymore. Answer is a fraction times m because you got the hole. All right. Oh, crap. So, all right. You might think how you would do that. Maybe I'll just start by saying I know that the mass of the disk, the solid disk, should equal the density of the disk times the area of the disk. And I hope you agree, we know the mass. You could get the area because isn't that just pi capital R squared? And so from this, you should be able to figure out the sigma. You can get the mass density. Then once you have that, mass of the final or whatever after the hole, I'll just say after hole. The mass after the hole should be the same density because it's made of the same material times area total or area disk minus the hole, area of the hole. And I'm going to put some parens around there. So hopefully that makes sense. That's how you can get part A. And my apologies if I stole your thunder. All right. And now, how would you get this? I sketched it out. We're looking for the center of mass position, right? If we don't have the center of mass position, you can't do a swinging motion problem. How do we do that? With the hole. Whoops. I could do radius center mass is going to equal x1 mass 1 minus the hole, x2 m2, right? All over m total. And because we did part A, I think we know the mass of the entire disk. That's capital M. We now know mass after the hole is cut. I know the center of the entire disk is at 0. And I know this one is at right here, right? And what is that? Isn't that just R over 2? Because it tells me right here. So this is going to be R over 2. And notice the hole is centered at positive R02. Excuse me. The hole is centered at positive R over 2 right here, positive R over 2, which then, because of this minus sign, you're going to get a negative number for the center of mass, which is what we expected right here. Now, if you wanted to get the radius, you could just slap an absolute value on this, right? Because we don't want a negative radius. So the radius to the center of mass would be the x coordinate absolute valued. Again, just in case there was lag, the radius to the center of mass is the x coordinate and then absolute value it. And then I saw there's a question. I'll hope Trey's getting that. Oh, nice spelling, Rob. That's cool. All right. Moment of inertia after the hole is cut. Don't think too much. I total, and I will check the chat eventually. I total is going to be I of the solid disk, the entire disk, minus I of the hole. So when you have a hole, it's just basically the same thing as adding two pieces, but you subtract them now. Now be careful. Remember, this one is going to have that mass after. And this one is going to use mass m. And I think these are going to be 1/2 mr squareds. And this one's going to be a 1/2 mass after. But then you got to put in, I think it's r/2 squared, because this one's got a different radius. So blah, 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 blah. And I'll show the full solution in just a second. And I will get to the chat in just a second. Counting on Trey there. All right. And so this is setup, setup, setup. Now you do an energy problem. Woofta, right? So this is actually fairly common for exam questions where parts A, B, and C might be do a center of mass problem, figure out a moment of inertia, deal with the hole and the density crap. Now part D means do an energy problem. And so it can seem really intimidating, but you have done all those pieces. Chapter 10 feels so difficult because you have to do so much work on center of mass and moment of inertia before you can do anything useful. All right. Hey, all right. I'm going to pause for a second, come back to this and see, check it with the chat. Okay. Okay. So let me see. Shouldn't the question state that the smaller hole? Okay. I think it sounds like you got that. Okay, cool. Looks like that's good. And then let me check one other thing here. And yeah, so and to be clear on questions like these, there's kind of a practical thing too, which is worth pointing out. Hopefully you all agree that if you cut this, it would be, you'd have to do this very carefully. Otherwise, the pivot point that you put in there would just fall out. Now, it turns out you can actually do this. If I blew this up, right? So that's, I'm trying to do this right. And then what we did, like, let's say we cut out a hole like this. Whoops. Sorry. Let me fix this one more time. And we take out this hole right here. I don't know if I can move that over there, but whatever. So it's not perfect. Sorry about that. And now if you cut out a separate hole right here for your bearing, right? You could actually do it just about like that. And so there'd be a tiny little gap there to hold the bearing in. Or even if you go all the way over, right, like that, you'd still have all the wood in this, or I guess I'm thinking wood, but you could use metal and that would probably be smarter. But you'd have all this metal right here keeping the bearing from falling out. And so even if there's a little hole there, because the pivot is non-zero in size, it could actually stay in there. And this is actually a totally possible thing. And in case you're wondering, is this just something stupid that a physicist would make up? You might not see this, but when I see this, what I'm actually thinking about is this is a camshaft to me. Imagine you actually have a shaft here, and then you're going to put lobes on it that are a cam, which are controlling the pistons in your engine. And so weird stuff like this could actually show up. Maybe not this exact problem, but the kinds of things that we're doing here do relate to practical design applications. It's just we get so buried in the details, you'll never see it. But there are practical applications to all these weird shapes with holes in them. All right, let me leave it at that. All right, and I'll go back to here and see if there's anything there. Okay, cool. And now one more question, everybody. You're tired, you're bored. Let's pay attention to parts D and E and think about you passing your test, okay? Now, I don't want you to solve part D and E right now, but I want everybody to read them and think about what type of problem you should do. Don't think about solving it. Just think, what tool should I grab? Okay. And in particular, because this is chapter 10, I want you to think about, are we going to want to use kinematics? Are we going to want to use torque? Or are we going to want to use energy problems? All right. That's really what you should get out of this part. I'll give you a second. Think to your neighbor. Or, well, I guess, yeah, do whatever you do. Okay. Rotation rate. Energy. That's what I was hoping you would think. Why? Because it doesn't have the word acceleration. Gee, I wonder what the other one's going to be. Angular acceleration, torque. Now, I think I was talking with Alexis before class. You got to be careful. You might think you could use kinematics here, right? If you're wondering, the answer is still no. Anytime you have swinging motion, do not do kinematics, okay? Do not do kinematics for swinging motion. You can do it for rolling motion. You can do it for yo-yo problems, which are next. But, and you can, I think, even do it for pulley problems, but not for swinging motion. So just, if you have a swinging problem, alpha not constant, don't use kinematics. I'm going to say that again. Swinging motion, alpha not constant, don't use kinematics. All right. I'm going to stop for a minute, and I'm going to go ahead and end the live stream for a second, but stay on and answer questions before we take a break.